Mesdames, messieurs, bonsoir pour cette soirée de jeudi qui est déjà l'avant-dernière de ce colloque Wright pour la science dans sa 21e édition qui se déroule toute la semaine à l'Université de Genève. Merci d'être venus nombreuses ce soir à l'université. Merci également à toutes les personnes qui nous suivent en ligne. Si vous étiez déjà présent au début de la semaine, vous me connaissez déjà. Je suis journaliste scientifique, mon nom est Sarah Serondada et j'ai l'immense plaisir d'être avec vous toute cette semaine jusqu'à demain encore pour animer les discussions. Bon, vous connaissez maintenant le principe. Chaque soir, nous accueillons un ou une scientifique de haut niveau pour nous accompagner dans ce voyage à travers les symétries de l'univers. Et ce soir, il sera bien question de l'univers de A à Z, du Big Bang, mais également des grandes questions en suspens, comme l'évolution et le devenir de notre univers, et ces grands mystères comme l'accélération de l'expansion, la matière noire, l'énergie noire. Et pour nous en parler, nous aurons l'immense plaisir d'accueillir Edmund Copeland. Il est professeur à l'Université de physique de Nottingham au Royaume-Uni. Mais avant de l'accueillir et de l'écouter, je vais vous donner quelques petits rappels pratiques que vous connaissez peut-être si vous étiez déjà là, mais que je vais quand même vous rappeler. La soirée se déroule en 2 temps. D'abord, l'exposé scientifique du professeur Copeland, qui va durer environ 40 minutes, puis un panel pour les discussions, où le professeur Copeland sera rejoint par 2 autres conférenciers des autres soirs de cette semaine que je vous présenterai tout à l'heure. Cela permettra d'élargir un petit peu les discussions et de répondre à vos questions. Là aussi, ça va durer environ 40 minutes. Et je vous rappelle que vous avez 2 façons de poser vos questions. La première dans la salle, en nous faisant signe pour avoir un des micros qui va circuler. N'hésitez bien à bien lever la main bien haut pour que je puisse vous voir. Ou à distance, en passant par la plateforme Slido et par le QR code qui s'affiche juste derrière moi. Vous pouvez poser vos questions pendant la conférence, sans attendre, si vous passez par la plateforme numérique. Petit rappel aussi, dans les 2 cas, vous pouvez vous poser vos questions en anglais ou en français, puisque la conférence de ce soir va se dérouler en anglais. Elles seront traduites dans les petits casques que vous avez pu prendre à l'entrée tout à l'heure. Petit rappel pratique à ce sujet, merci de ne pas monter le volume de vos casques trop fort pour ne pas gêner vos voisins. Merci également de bien vouloir éteindre vos téléphones ou les mettre en silencieux par respect pour les conférenciers, pour pas que ça sonne pendant la conférence. Merci beaucoup. Et avant d'inviter sur scène l'orateur de ce soir, je voudrais donner la parole à Camille Bonvin, cosmologiste et professeur de physique à l'Université de Genève et membre du comité scientifique de la Fondation Wright, qui va nous présenter et inviter sur scène le professeur Copeland. Merci beaucoup Camille.
Bonjour à tous, bienvenue à cette 4e journée des Colloque Wright. Donc aujourd'hui, j'ai le plaisir de vous présenter le prof Edmund Copeland. Donc Ed a obtenu son doctorat en 1985 à l'université de Newcastle et il a travaillé ensuite à différents endroits. Il a travaillé à l'Imperial College à Londres, au Fermilab aux États-Unis et puis il a ensuite été professeur à l'université de Sussex et il est maintenant professeur à l'université de Nottingham. Et Ed fait partie de ces scientifiques incroyables qui font avancer la recherche et laissent leur marque dans des domaines extrêmement divers, avec beaucoup de talent. Il a travaillé par exemple sur la théorie des cordes, sur l'inflation, mais il a aussi travaillé sur les ondes gravitationnelles, qui sont ces petites déformations de l'espace-temps qui se propagent dans l'univers. Il a travaillé sur l'énergie sombre, qui constitue peut-être 70% du contenu de l'univers, mais aussi sur la matière noire, qui constitue très probablement 25% du contenu de l'univers. Et il a travaillé aussi sur les trous noirs et sur les théories de gravitation modifiées, au-delà de la théorie d'Einstein. Et dans tous ces domaines très divers et très vastes, il a eu un impact décisif. Et il a supervisé et guidé de nombreuses générations d'étudiants. Et en fait, souvent, avec mon groupe de recherche, on fait des recherches pour avoir une information dans un domaine particulier et on tombe sur un article scientifique d'Ed qui a posé les fondements dans ce domaine. Donc Ed a eu pour sa recherche de nombreuses distinctions et supports. Par exemple, en 2013, il a gagné la Riley Medal pour son travail sur la théorie des cordes. En plus de cette recherche extrêmement vaste et de pointe, Ed est aussi, comme vous allez le voir, un communicateur exceptionnel. Il a en fait une chaîne YouTube qui s'appelle 60 Symbols, qui est vraiment incroyable et qui parle un peu de tout. Et j'avais envie ce soir, pour vous allécher un petit peu, de vous citer certains des titres de ces vidéos, comme par exemple « Où sont les trous blancs ?», la fameuse bourde d'Einstein, l'énergie sombre et le grand déchirement, mais aussi « Qu'est-ce qui rend un physicien confus ? Est-ce que Brian Cox avait tort ? Quel est mon physicien préféré ?» Cette chaîne YouTube, c'est vraiment un bijou de science qui reflète l'incroyable connaissance d'Ed dans des domaines extrêmement variés. Et tout à l'heure, avant de venir, j'ai regardé les statistiques de cette chaîne YouTube et j'ai vu qu'il y avait 888 000 inscrits. Donc pour une chaîne qui parle de sciences fondamentales, je pense que c'est quand même assez fou. Et puis, il y avait 404 vidéos. Alors certains d'entre vous vont peut-être voir une symétrie cachée dans ces chiffres. Ce soir, Ed va nous parler de cosmologie, et je ne crois pas que durant cette semaine, on a déjà donné la définition de ce qu'est la cosmologie. La cosmologie, c'est l'étude de l'univers. C'est un petit peu différent de l'astrophysique, qui étudie les phénomènes dans l'univers, alors que la cosmologie s'intéresse aux propriétés de l'univers dans son ensemble. Et en fait, le début de la cosmologie moderne est intimement lié avec Einstein lui-même. Parce que depuis Einstein, on a une théorie, la théorie de la relativité générale, qui nous permet de décrire l'univers. Pas seulement les objets dans l'univers, mais l'univers lui-même comme une entité qui évolue. Donc ce soir, Ed va nous parler de l'histoire de cet univers. Et quand on étudie l'histoire d'un pays, l'histoire d'une personne, on aime bien parler des événements importants, curieux, bouleversants qui se sont passés dans leur passé. Eh bien, Ed va faire exactement pareil, mais pour l'univers. Il va nous dévoiler tous les petits et les grands secrets de l'univers. Donc, merci d'accueillir chaleureusement le professeur Ed Copeland sur la scène.
Okay. Wow. Bonsoir. Good evening. Thank you for coming, and I hope you have a good time. That's the most important thing, that we have a good time. I'd also like to thank Camille. So she comes on and she introduces us. She's actually a world-class cosmologist in her own right. so thank you, Camille. And thank you to the interpreters for the talks that have been in French. I don't know how they've managed to translate them into English. So I'm hoping that they can do it going English back into French for you. So today I'm going to try and tell you about some ideas about the universe. There's lots that we don't know. So for those young ones amongst us, I still count myself young at heart, then there's lots to be done. So this picture that you can see is probably the first picture of the universe. It's the equivalent of taking a picture of seeing the picture of a 100-year-old person taken when they were a day old. It's the baby picture. This is the moment that the first atoms were forming in the universe. Our universe is about 13.8 billion years old, we think. These atoms were formed when the universe was about 380,000 years old. And why was that an important event, apart from the fact you were forming atoms? At that moment, the radiation that was present in the universe, the photons of light, could begin to propagate. So off they went. And they just went. And they've been coming all the way for 13.4 billion years. And then in around 2009, they landed in the detectors, the bolometers, of a satellite called the Planck satellite. And the Planck satellite was up in the sky, doing searches around the sky and looking at the radiation that was coming into it and taking the temperature of that radiation. You can see on that image small red dots and small blue dots. I want you to keep just a mental picture of how big those dots are, because we'll come back to it. These dots are representing incredibly small amounts of temperature rises. There's a background of 2.7 Kelvin. Kelvin is that's a really cold universe. So ice freezes at 0 Celsius, which is 273 Kelvin. The background radiation that this Planck satellite was detecting is 2.7 Kelvin. What you're seeing are the small fluctuations, the little ripples above and below that 2.7 Kelvin. The red and the blue dots are increases and decreases of about 1/10,000th of a Kelvin. Okay? This is why structures form in the universe. This is why you're here. Okay? And we're going to have fun just trying to get there. Sound okay? Let's go. So, I've already said it. The goal tonight, then, I'm going to try and convince you that there's a link between the events that occurred in the first fractions of a second of our universe and the universe that we see today on the largest possible scales. I'm going to try and connect them. So, events occurring way before the first second have left an imprint in the universe some 13.8 billion years later. So when you go out, and the last few days haven't been particularly clear in the sky, but on a nice clear sky, and you look out at the distant galaxies, then remember, what you're seeing is a thumbprint of the very early universe. So all that you need today is a healthy imagination, okay? As long as you've brought that with you, we're okay. There are many scales in our universe, so let's try and base ourselves on things we know, and then we'll get bigger, and then we'll get smaller. So here's probably the most iconic picture ever taken of the Earth, right? This is Earthrise from the Apollo 8 mission taken on the 24th of December, 1968. It's a picture of the Earth. And I really love the thought that most of us are in that picture, right? We're there somewhere. We might be on the wrong side of the Earth, but we're there somewhere for many of us. And it's there simply so we can talk about scales. So the Earth is about 12,000 kilometers across, okay? That's the diameter of our Earth. Our Earth orbits the sun. And the sun has a diameter of about 1.5 million kilometers. So the Earth is 12,000. The sun has a diameter of about 1.5 million. And then the typical distance between the sun and the Earth is about 150 million kilometers. And these numbers begin to get so big that we begin to introduce new units, right? So this is called an astronomical unit. It's the typical distance between the Earth and the sun. And our sun is part of a solar system. And I took this photograph for you of the solar system. I didn't. One of my concerns is that my jokes may not work. But I can't my solar system had Pluto in it. I don't know if yours did. My solar system, I'm afraid it still has Pluto in it. I can't let Pluto go. The typical size of our solar system, right? The distance between the sun and Pluto, the average distance, is about 5.9 billion kilometers. A billion is 1,000 million. This is about 40 astronomical units. And if I got this right, last week, NASA managed to reconnect, I think it was with the Voyager mission, which they'd lost touch with, and the Voyager mission is basically there at the edge of the solar system, about to shoot off into the deeps of the comet world. So our star, which is protecting us, is one star within a galaxy. And our galaxy, of course, is the Milky Way. And the Milky Way is a spiral galaxy. But you can't go above the Milky Way to take a picture of the spiral arms, so that's why I've got the Whirlpool galaxy there, so you can see what typical spiral arms look like. The picture on the left is the Milky Way. And we live towards the edge of one of these spiral arms. The typical diameter of a galaxy is now, we're getting to huge numbers, right? 100,000 light years. So a light year is the distance light travels in 1 year. Light travels 300 million meters per second. So this is the distance it travels in 1 year. The typical diameter of our galaxy is about 100,000 light years. And that's about 10 trillion kilometers. One galaxy so far. What our galaxy, we think, has roughly 200 billion stars in it, as well as our sun. This is the first time where I think it's important to tell you, these are models. No one's ever counted 200 billion stars. Okay? 1, 2, 3, 4. Oh, 1, 2. Okay? We model things based on what we can see around us. And this is an important element that will come into when we're trying to understand our universe. They're based on models. We live in a universe that's filled with galaxies. This is such an amazing image. This image was taken by the JWST telescope, which was launched about a year or so ago. It's looking back about 13.4 billion years. It's the furthest that we can see in the universe. And there's a couple of things I want to point out to you here. Can you see the silver bits? The thing that's got all the lines coming from it, that's a star. For once, let's not worry about that. I want you to look at sort of the silver-looking cluster of galaxies. They're a cluster of galaxies, so quite a few galaxies. And they're so massive as a cluster that what they do is as light comes past them from distant galaxies, the light gets bent. And that leads to images. And can you see arcs in this picture? Can you see those orange-looking arcs? They're distant galaxies, right, that have been lensed. And within some of those arcs, you can actually see stars, which is just mind-blowing that you can do this. And this is one of the ways that we're going to be testing for the presence of what we call dark matter, by looking at the distribution of these arcs. Because what you can do, remarkably, is given a distribution, we can reconstruct what the matter must be in the vicinity of those clusters of galaxies. Okay? So this light that you can see has been traveling for about 13.4 billion years and reached us. And it's in the infrared because the universe is expanding. So when the light left those distant galaxies, it might have been in the optical. But as the universe expands, if I have a wavelength of light and the universe expands, can you imagine the wavelength stretches? And it moves into the red part of the spectrum. And eventually it moves out of the red bit that you can see and into the infrared. And that's why this telescope is so important for those of us who are interested in the early universe, because it means that light that was emitted in the early universe can be picked up by this telescope because it's stretched into the infrared today. It looks like the universe is full of matter, but the universe is really, really big. And I want to give you an idea of the density of matter in our universe. And I was trying desperately, how am I going to do this? If you take a grain of rice, you've all taken a grain of rice, you've probably spilt a grain, many grains of rice, right? Take a grain of rice and ask, so you can take the mass of that grain of rice, and the density is the mass divided by the volume. That's what the density means. Ask yourself, how big a volume do I need to have so that this grain of rice is representative of the universe on average? It's the size of the Earth. Your grain of rice is there alone in a region the size of the Earth. And then there's another region beside it, the size of the Earth, with one more grain of rice in it. So the universe is pretty empty overall, which makes it really important that we understand how structures clump together to allow galaxies to form. Okay, so we try to understand our universe. I've just described what it looks like. We try to understand it. And the person that we turn to is the genius who was Albert Einstein. And in 1915, he published his general theory of relativity. And we were fortunate enough to hear Jean-Philippe tell us about this. But here's an interesting thing I think about this period. Right? In 1915, he knew about the Milky Way. You could see it, right? You could see the stars. You could see the Orion's belt. You could see the various clusters of stars moving around. He didn't know about galaxies. People did not know about other galaxies. They could see what they called nebulae. They could see these sort of phasey things which seemed to have some extent, but they didn't know what they were. And why is that important? Because within a few years of him publishing this theory, two physicists, Alex Freeman and Georges Lemaitre, who's a priest, realized that applied to cosmology, his equations told you that the universe was either expanding, getting larger, or contracting. But it wasn't static. So this didn't please Einstein. In fact, he said to Lemaitre, Lemaitre, he agreed with his results, his calculation. He said, your mathematics is fine, your calculations are correct, but your physics is atrocious. In other words, your result may be there, but it doesn't apply to our universe. And in fact, and one of the reasons he believed this was that you looked out in the sky and you didn't see the stars moving apart. They were always at the same relative position. So he did something which has turned out to be really crucial. He added a term to his equations. He was perfectly allowed to add it. It satisfied all the symmetries that his equations demanded. This was called the cosmological constant. And this term, he had to make the universe curved. With the curvature, this term made the universe static. He'd done it. Okay, we're back. We've got our static universe. However, Eddington pointed out to him that his solution was unstable. This amazes me, right? All of us who work in this field, or in any field where you're solving a dynamical system that's evolving, and you get a solution that's stable, you ask yourself, well, you get a static solution. The first thing you say is it stable? So if I perturb it, will it go back to my original solution, or will it start evolving? Einstein must have done this. He absolutely must have done this. And I think he must have thought, I don't like that result. And so he ignored it. I mean, otherwise I can't understand. I mean, this is the most brilliant scientist probably of all time. And he didn't do this. We set this in our undergraduate cosmology problems sets to demonstrate this universe, that this is unstable. And in fact, in June 1930, he visited Nottingham to give a lecture, and I like to think that he was probably worried about this issue. He certainly forgot to bring any money, and his wife at the time had to pay for everything. There was a very bright person, a wise move was made. He gave a lecture in Nottingham in German, and no one in Nottingham did physics, no one there did mathematics, and he gave this very technical lecture, but someone realized, actually it would be a good idea to keep the blackboard, and they got him to sign it. So if you ever come to the university at Nottingham, you can see a blackboard signed by Einstein with all of his equations on there. So in 1929, Edwin Hubble answered the issue. He demonstrated, using the Mount Palomar telescope, he could look deep enough into the universe, and he saw that distant galaxies were moving apart from us. And that was evidence that, as Lemaitre had shown in his equations, that the universe was expanding. And Einstein believed it at this point. And the relationship is that the velocity of these distant galaxies moving apart is proportional to their separation. So if you double the separation, you double their relative velocity as they move apart. It was a result that Lemaitre had shown, so we called it Hubble's law, of course. So it marked the beginning of what we call modern observational cosmology. There was now no need for Einstein's cosmological constant because now the universe was expanding. We had a universe that contained radiation coming from all the objects that were emitting light. We had a universe that contained matter, you and me. And when you solved Einstein's equations with that, that universe would expand but would slow down. Gravity sucks. If you're always trying to think which way gravity works, gravity always sucks, pulls you back, okay? So we had a universe that was slowing down, and it all made sense. I remember as a PhD student in 1985 hearing talks where they were presenting evidence that the universe was perfectly consistent. Everything was in matter, and the universe was decelerating. That's slowing down. But then, such is the way that we work in science, we're always pushing, we're always trying to see if the theory really survives tests. So there was a group of astronomers looking on very large scales, looking at galaxies and looking at what they call the angular distribution function, correlation function. How were galaxies on the sky positioned relative to one another? And then when they tried to fit the data with this model of a universe dominated by matter, it didn't fit. And people began to realize we might need this cosmological constant again. And in fact, in 1992, a friend of mine, George Eustathiou, wrote a paper, a Nature paper, in which he suggested this data suggests there needs to be a cosmological constant. Most of us ignored it. Some listened to it, but most people ignored it. And it wasn't until 1998 when the two groups of observers looking at distant supernovae exploding in galaxies. So a supernova is an exploding star, and there's a particular type of supernovae called a type 1a supernovae, which has wherever it is in the universe, we think it's the same physics that leads to it being exploding. This makes it what we call a standard candle. It means we can trust it, the light from it. We know how much light was initially emitted. And if you have a standard candle, it means you can look at the relative brightness of an object, and that tells you about the distance to the object, okay? So we had a distance scale from these supernovae, and then you fitted it. We could always measure the velocity by what's called the redshift of light. You experience redshift all the time. I did. I had a real fright today going into the department when a fire engine went past. You know that sudden shift of tone? When it goes, it shifts as it goes past you. The wavelengths get compressed and stretched as they come towards you, compressed and stretched as they go away. The same thing happens with light. And if objects are moving apart from you, the light from the objects is getting redshifted. And you can measure that, and that determines the velocity. So we can have our Hubble diagram again. And I've only put it on here so you can actually see it's a pretty linear fit for the low redshift or low velocities, and then it begins to deviate a little bit away. And this was regarded as the evidence that the universe was A, accelerating, and B, had this cosmological constant. So before we go into the details of this acceleration, which is, we don't know what's causing it. So if you don't know what's causing it, you call it dark something. We don't know what's causing the acceleration, so that's dark energy. We don't know what most of the matter is in the universe, that's dark matter. But you and I, we make up 5%. So we're all right. We're all right. We know what 5% is. Let me just revisit what we think is happening on very small scales. So you've seen this twice now. Yasmin's beautiful talk yesterday, she went through this, so I won't go through it in detail. So we have what we call the standard model. The standard model is made up of quarks. The quarks combine to make up our protons and neutrons. and then the leptons. And the most famous lepton is the electron, okay? There's also these wonderful, weird and wonderful particles called the neutrinos. And they're emitted from the sun, they're emitted cosmologically, the sun's pouring out neutrinos. I mean, have a look at your thumbnail. There's about 1 billion of them going through your thumbnail every second. So if you feel a bit itchy, you know, you never know. It might be a neutrino just... They don't interact. That's the real evidence that they don't interact very well, right? They're passing through you and they don't care about you, passing straight through the Earth. But it's actually become a fantastic area of science. Neutrino astronomy is growing as an area. So we've got our ups and we've got our 3 generations. Can you see the green, the blue, and the red? Why 3? Why 3? You and I just are made up of up and down. We only need 1, really. The others are there. Are they there for the ride? No, they're vital. Without it, the world wouldn't be here. But they don't play such a major role in our everyday life. We don't know why there are 3 generations. Why not 4? We don't know the masses of the particles. Well, we do know the masses of the particles. We know them exquisitely. That's why the standard model is such a great model. We've never been able to predict the relative masses of the particles. We don't know why they've got the masses they have. So then, with the masses of the particle, with the particles themselves, the matter side, you've got the forces. And those were Daniel gave that amazing talk where he described the symmetry properties of the bosons that give us the forces. And so you've got the photon, which is why we can see each other today. We've got the vector boson, the weak force, which is why the sun is burning. We've got the strong force, the gluons. Do you remember him telling us about that? Which basically is why you don't explode. And then we've got gravity, and we've never seen a graviton, a question that was asked. We think the graviton is there, it's the quantum mechanical particle that delivers the force of gravity. And then we've got the Higgs. The Higgs that was discovered just on your doorstep here at the LHC. And that's the particle that gives the masses to these fundamental particles. Okay? And then, of course, the whole essence of that wonderful talk yesterday was the antiparticles. We've got antiparticles for each of these, but where are they? How come we fortunately, they've gone. Otherwise, we wouldn't be here. But we still don't really know the mechanism which led to them being eliminated. So here's the Higgs. Here's a Higgs discovery. This is an actual event taken on when is it? May the 13th, 2012, at 20:08, okay, in the evening. What were you doing then? The LHC, they were finding this Higgs candidate. The Higgs is formed from the collision of the protons, and then it lasts, by the way. It's not as if it says, here, I'm here, look at me. It lasts about 10 to the minus 20 seconds. It's very shy. And it's gone. And it emits these 2 photons. Particle physics is the ultimate jigsaw puzzle. You get the debris, and you have to reconstruct the collision. We came, Camille was very kind, by the way. I think you were. I didn't understand half of it, but we do these videos, so we came to CERN, and it was closed. So no, we'd arranged to come. So we went up into the hills, and we thought, actually, we can produce our own collisions. You can quite easily collide billions and billions of protons. So I don't know if this will work, but I'll just show you my experimental, what a great experimental physicist I am.
A regime where the Higgs could be produced.
Don't worry about the
You
words.
actually would
not
get
the
one
part.
Higgs in
But,
every
you'll see
10
the
trillion
and I think
events.
you'll get the idea of there you go.
That sounds like you'll never get any Higgs. But remember, you've got
there's your particle
up
physics
to
experiment.
a billion events a second, collisions a second happening.
Debate on the next generation colliders. I mean, you just
It
just
actually
do
means
it, right?
that you
There
could get a
go.
Higgs
Right.
maybe once every 3 hours.
Okay, let's not worry. So, we've got the particles. Where did the first nuclei come from then? An atom is made up of a nuclei and electrons going around it. The nuclei formed within the first few seconds, the first minute or two. The simplest one to form is hydrogen nuclei. It's a simple proton, one proton. So most of the matter that you can see in the universe is hydrogen. The next simplest is helium. So most of the remainder, so around 95% of the visible matter in the universe is hydrogen and helium. And in fact, there's so much hydrogen formed in the first few minutes that the chances that when you drink a glass of water, there's a bit of hydrogen from the early universe is quite large. So if you think it tastes a bit funny, it's very old. Okay? And the stuff we are made of, I'll just reiterate it one more time, the protons, the neutrons, the electrons, makes up about 5% of the total energy density. And now that gave me a chance for a gratuitous photograph of Taylor Swift, because I went to the concert in Paris. So my daughter got us tickets, so we went. And she's everywhere, and even she's only part of the 5%. What about the heavier elements? What about the carbon, the nitrogen, the oxygen? This is a great story. These come from stars. They're processed in the stars, not in the early universe. And so but you've got to get them out of the stars to get them into the planets later on. So you're stardust. The stars have to explode. And for the gold, you need many, many situations where you form a star, it explodes, it recollapses, forms a bigger star, keeps going, in order to process it so that it can create gold. So those of you that have got, say, gold rings, you're multi-stardust people. Okay? So I said the universe was full of this radiation, and that from when the first atoms were forming, and it was released. And it's beautifully isotropic. That means it looks the same whether it came from that direction of the sky, or this direction of the sky, or from up there. It's exactly the same temperature to within those small fluctuations that I mentioned. And this was measured by a phenomenal experiment called the Colloque satellite, which went up in 1992 and discovered this perfect black body spectrum. This is their data, and the error bars are smaller than the width of the line. It's just a staggering piece of data. And so it's the universe that tells you, it's the result that tells you that we're bathed in this radiation, which has cooled down as the universe has expanded, and cooled down to a temperature of about 2.7 Kelvin. So the model that we're using, and it's a model that we call the Big Bang, basically has various assumptions. That on very large scales, the universe is homogeneous and isotropic. It looks the same. Isotropic means you're in no special place. So if you make a perfect fruit pie, a fruit cake, okay, all the fruit is distributed evenly throughout the cake, right? If I make a fruit cake, it's highly inhomogeneous. The fruit is at the bottom. But a perfect fruit cake is beautifully homogeneous. Do you get the idea? So if you take a slice of a fruit cake and just looked at a small bit, you wouldn't know where it was from the bottom or from the top. That would be the idea. So the universe on large scales is homogeneous, it's isotropic. And then if I put in some initial conditions, which have some particles that are expanding out, I don't know what banged, but some particles are expanding out, coupled with Einstein's general theory of relativity, then it tells me that the universe will be expanding, it'll give me Hubble's law, it'll tell me when the lightest nuclei form, it'll tell me that I'm bathed in this radiation with this temperature that I see today, and the universe is old and large, about 13.8 billion years old. But crucially, it does not tell me where the structures came from. And we need to know that, right? Because we're here. So the early universe, what we believe was it was not perfectly homogeneous, and that there were small ripples. And these small ripples are like, when you go up into the Alps and you go to one of those magnificent towns and you look from a distance and everything looks beautifully flat. When you go really, really close, you see little ripples. I'm talking about that kind, and this is the little ripples in space-time that happens. And once you've found that, once you've got these little ripples in space-time, which then lead to little ripples in the matter, Sir Isaac Newton will do the rest for you. It's got to be Sir Isaac. He's from near Nottingham. I've got to show some solidarity with my local genius. And gravity will pull. So where there's a slightly excess of matter, the gravitational pull is stronger, and it pulls matter in. Where there's a region devoid of matter, there's less gravitational pull there, and it will lose out to the neighbors. And so that's where you get the picture that I showed at the front, the Planck one, and then the picture on your right is called the Sloan Digital Sky Survey. Each dot there is a galaxy. Okay? Each dot's like the Milky Way. Can you see the structure in there? There's like voids and then surfaces that seem to have higher densities of matter on there where the galaxies are. And the idea is that's an imprint of those initial fluctuations. So what caused those initial fluctuations? We think it was a period in the very, very early universe of inflation. Inflation is simply defined as a period where the universe accelerated. It grew effectively exponentially fast. And so I want you to, when you look at this picture, you think of the very early universe as at the bottom of the picture, that tiny blue region. That tiny blue region is so small that the light within it has had a time to interact. So everything in it has managed to meet each other. Hey, how are you doing? Yeah, what temperature are you? Oh, I'm at the same temperature. Everything's uniform there. And then for some reason, the universe suddenly increases in size exponentially rapidly. So it grows by a factor of, I wish I hadn't have done that, 1 billion, billion, billion times in a time of 1,000,000th of a billionth of a billionth of a billionth of a second. Okay? That's the idea. Healthy imagination, okay? That's the idea. And the effect of that is our observable universe, which is the red bit of there, is now beautifully flat, beautifully smooth, isotropic, homogeneous, and it has crucially these small little perturbations that I need to form the structures, because the thing that was responsible for inflation, so there's just a nice picture, trying to show you that it makes the universe look flat. You know, if you're on a beach and you look out, it looks flat to you, right? Even though you know, well, I hope you know, there's a curvature to the Earth, right? And, all right, I didn't mean I hope you know, I hope you believe. No, I know you know. But there were fluctuations in the field that was responsible for this inflation. Quantum fluctuations. Do you remember Daniel telling you about the uncertainty principle? And this uncertainty principle means that you never can quite tell where something is and its velocity at the same time. So there are fluctuations in it. And that fluctuation is what leads to the fluctuations that we see in the microwave background, the anisotropies. And so these fluctuations are occurring at, I told you the scale, right? 10 to the minus 30 seconds after the Big Bang. And these are the things that provide those initial conditions that lead to the hot and cold spots in the cosmic microwave background. And it fits the data really well, okay? I'm just showing you that to show you what that's the data. Do you remember I asked you to keep an eye on the size of those spots? Can you see that the peak of these fluctuations are occurring on 1 degree? That's the typical size of those hot and cold spots that we saw. And that's where all the power is. And that's what this is measuring. So what about the majority of the matter? How do we see it? Well, we see it through gravitational lensing. And it blows my mind when I think about this. All that we really have to play with is light. Light coming from distant objects and being bent. Light of different wavelengths, different frequencies, different intensities, and we can concoct a model of the universe based on this. And we look at the light, and from seeing how much light gets bent, we can infer that there's about 25% of the universe is in what we call dark matter. Matter that behaves like ordinary matter, it just doesn't interact electromagnetically. You can't see it with light, hence it's dark. And we think that's out there. And I think how long do I have? I've forgotten. Am I okay? I'm okay still? Yeah? Are you okay? Have you had enough? Okay. So it can't be ordinary matter. It can't be you and I. Why can't it be you and I? Because you and I interact with electromagnetism, right? Photon, I can see you. Well, I can't see you at the back, the lights are really bright. But light bounces off us, and so we interact with each other electromagnetically. So the dark matter can't be the stuff that you and I are made of. It would have to be something else. And so there are lots of candidates. They're called WIMPs or axions or maybe primordial black holes that are out there. Here's a dark matter zoo for those of you who like zoos. Look at the range of masses. You don't even need to worry about the universe. Can you see on the right-hand side of this, it's going to 10 to the 30. On the left-hand side, it's going to 10 to the minus 21. That's 51 orders of magnitude. We've got a large span of particles that could, in principle, be the dark matter, and they're ranging in these scales. You'll even notice there's a break between particle-like and wave-like. Those are your fermions, are your particle-like, and your bosons are wave-like. There's a lot of work out there for you to do, for those of you who are interested in trying to understand the nature of dark matter. Okay, I've told you that. The evidence for dark matter, well, here's one piece. Galaxies are rotating, and you can measure the speed of rotation at different distances away from the center of the galaxy. So here's the center, my fist, and you can measure the rotation of objects at different distances away. Now, if the light bit of the galaxy was all that you saw, was all that the galaxy was made of, you'd expect the velocities to rise to the edge of the light region and then drop. And that's the bottom curve where it says expected from visible disk. But look what happens. The data has it going to a constant, or rising slightly, which suggests there's something else there that you can't see. And this was a phenomenal physicist, astrophysicist called Vera Rubin, was the first person really to realize this. I won't show the simulations. I'll instead go on to gravitational waves, which is a new area of cosmology. So they're a new frontier. They were predicted by Einstein in his general theory of relativity. They are the distortions of space and time. So if you wave your arms around, don't listen, just do it. You're creating gravitational waves, okay? You're doing it. It's just that they're not very intense. Fortunately, you don't feel them. If, on the other hand, you have huge black holes merging together, they create gravitational waves. And that was what has been detected by the LIGO people. So Einstein knew these, he realized these things were there, but he never thought they'd be detected. And I must admit, I don't think I did, really. I thought it'd be too difficult. But then in 2015, the LIGO consortium announced the discovery of gravitational waves using what are called interferometers, 2 interferometers in the US. These are long tunnels at 90 degrees to one another. The gravitational waves come in. Here they come. I happen to see one coming in. It hits one of the arms and then goes through and then hits the other. And it distorts. Because it's a distortion of space-time, it distorts the length of the interferometer. And that distortion can be picked up. And why I didn't think they'd be seen is that the amount of distortion is about 10 to the minus 17 meters. Just the nucleus of an atom is about 10 to the minus 15 meters, okay? So these are phenomenally small things, and they detected them. This whole experiment just blows you away. The black holes, can you see? Each black hole is massive. 30-odd solar masses of a black hole collides with one of 29 solar masses it combines to give you a single black hole of a mass of 62, and that releases about 3 solar masses of energy in gravitational waves. They then propagate for 1 billion years, and they come into the detector and they distort it by 1 part by 10 to the 17 meters. It's good, isn't it? And they've got hundreds of these now. So today, we're in a universe driven by dark energy. We don't know what the dark energy is. It could be this cosmological constant that's driving it. It still remains the best fit to the data. It's smoothly distributed. We don't really see evidence of it clustering in the way that dark matter can cluster. It's got a constant density, hence it's like the cosmological constant, which has a constant density. But crucially, maybe it isn't constant. Maybe it's slowly changing in time. And that's where the emphasis is today, to try and look for evidence that the dark energy is changing slowly with time. And so there are experiments out there to do that. And, it's a big problem, by the way. The theoretical prediction of what this should be is a mere 10 to the 120 times the observation. So if you lose a factor of 2 in your calculations for you PhD students, don't worry about it. When you've got a factor of 10 to the 120, it's more of an issue. Here again, the position of this first peak in this data of the cosmic microwave background tells you about the amount of dark energy. That's why we think there's about 70% of the energy density in the universe is stored in this dark energy, which is driving this acceleration. Remember what I mean by the acceleration? Distant galaxies are accelerating apart. You know from a car, right? If you accelerate, you're putting fuel into it. The dark energy is the fuel that's driving that acceleration. And we test for it. We look at our universe to see whether we can see any evidence that this dark energy is changing with time. And there has been recently an observation by what's known as the DESI collaboration, which tentatively suggests maybe it is. They're looking at combining supernovae data that I talked about with the cosmic microwave background data that I talked about. And when you do that and you fit it to the dark energy, the best fit, which is what you usually look for, is one that seems to have it changing with time. We wait and see. I hope it does. I wrote a review article all about it changing with time. So please change with time. But there's lots of telescopes. I don't know what the future is, by the way. So that bit's a very short bit of the talk. The universe could keep going. If dark energy if it remains dark energy dominated, it's not great news, but it won't affect you. Don't worry. We're talking many hundreds of billions of years in the future. Galaxies, we can currently see galaxies. They'll move apart. So eventually galaxies will go out of our field of view. And then eventually within the galaxies, the stars will start being pulled apart. And then within the stars, the atoms will start being pulled apart. It's not great. Okay? So let's hope dark energy doesn't last forever. Let's hope we get back to just that nice matter and radiation that we all know and knew and loved back in the 80s. Let's be nostalgic for those days. And, there's the universe timeline. That's the inventory. 70% dark energy, 25% dark matter, 5% ordinary matter. I want to finish on this rather, I'm really grateful that you've come. I thank you so much. But why believe a word of it? Okay? Why believe that I can talk to you about the first fractions of a second and then the evolution of structures in the universe when we don't even know how our brain makes decisions, for example? Okay? On much smaller scales. And it's for the following reason why I hope you believe it. We believe that structures emerge from those small fluctuations. I've tried to keep going on about these small fluctuations. Generally, if you've got something that's got small fluctuations, you can then solve for how those fluctuations evolve. Because then they're not very large, and so they'll grow very slowly. So you can solve for the growing of those fluctuations, and that's what I've been describing. Eventually, in cosmology, they'll start forming galaxies. then you're in trouble, because that's much more non-linear, it's called. The linear fluctuations become non-linear and much more difficult to solve. And indeed, galaxy formation is still not understood properly. An example of this is we know that we can use Newton's laws of orbit around the sun. We know with certainty there will be a full solar eclipse in Spain. It'll be on the 26th of August, 2026. It'll be in Valencia, right? Beautiful place. It'll begin at 20:32 and 27 seconds. It'll end at 20:33 and 28 seconds. So book your tickets, right? Unfortunately, it won't be till maybe even half an hour before. I've put 2 hours, maybe half an hour before you know you can actually see it because of the cloud cover. One of those is effectively the perturbations. The orbits of the planets is effectively perturbation theory. The development of clouds is, remember the butterfly effect? The development of clouds is non-linear, it's complex, it's non-linear. And in fact, it's chaotic. And that's the analog here, right? We're in the perturbation regime. So that's it. That's your tour. Thanks ever so much for listening, and I hope you've enjoyed it.
Thank you very much, Professor Copeland, for your talk. Summarizing the story of the universe in 40 minutes is not an easy task, especially when you add so many jokes in it, so thank you very much. It was really good, it was brilliant, and I hope the audience has been as fascinated by it as I have been. And it's now the time for our panel to start, so please have a seat. And I would like to welcome on stage Yasmine Amis. Elle est directrice de recherche au CNRS, au laboratoire de physique des deux infinis Irène Joliot-Curie, en France. Vous l'avez entendu hier, je suis repassée sur le français pour vous présenter nos deux intervenants. Et j'accueille également Enrico Cohen, professeur au département de cellules et biologie au John Innes Center à Norwich, au Royaume-Uni. Et vous aurez le plaisir de l'entendre demain sur la question des symétries en biologie. Welcome, thank you for joining us on stage. Et vous avez noté qu'on a rallumé les lumières dans la salle, ceci afin de mieux vous voir pour prendre vos questions tout à l'heure. But I will switch back to English for our talk tonight. And you know, I will start this Q&A as yesterday with a very short 5-minute discussion before we open the floor to your questions. My first question is to Ed. The main takeaway of your talk is that dark matter and dark energy's nature as what we don't know yet. And you showed us this slide with some current ideas, scenarios of what dark matter could be. So maybe could you elaborate a bit on the 3 ideas we have right now, and why do you prefer one of these?
Okay. Can you still hear me? So that slide, I think it had 10 to the 50 orders of magnitude. So on the right-hand side, the heavier particles, we think they're, the favorite candidates are called WIMPs. They are weakly interacting massive particles. So when I said they don't interact electromagnetically, they only really interact via the weak force, which is, as the name suggests, a very weak force. So they're very difficult to find. And one of the big hopes of the LHC, it had 2 main goals. One was to find the Higgs, and it did it. And the second was to find evidence of what was called supersymmetry, that Daniel talked about, the relationship between fermions, the matter in the universe, and bosons, the force carriers in the universe. Out of supersymmetry, these WIMP particles, they're natural objects to find. And we've not found them. There was we were pretty certain, I think, we would see something. I certainly remember in the 80s and early 90s, everyone being very sure they'd find it, and they've not. So what do? The evidence is there in the data that the lensing of light So there's two ways you can go. I'll stick with the matter. You could try and modify gravity. Say Einstein was wrong and modify gravity, but let me not go there now. So you try and think up other possible candidates. Black holes. Maybe black holes formed in the very early universe. They could be possible candidates. But more recently, the interest has gone over to another side, the very light particles, and things called axions. And axions are effectively like bosons. And if you remember Daniel telling us, fermions don't want to be together. You can't get two fermions on top of one another. Therefore, if you're going to have fermions being the dark matter candidates, you need them to be quite massive, because they're sort of living side by side, but they're not clumped together. Bosons, on the other hand, love to be together. They form what we call condensates. And so you can have very light bosons, which will clump together to give you condensates, which can become effectively the dark matter. And there's a huge amount of work going on into the axion side of things at the moment, not least because we think axions exist for another reason, which is to do with an issue in strong physics. It's called the strong CP problem. And then other theories produce lots and lots of axions. So we think it's worth looking for them. We haven't found them. We haven't found any dark matter directly yet, but you never know, right? So I think those are the three main areas, right?
Thank you. I now turn to Yasmin. So there could be a link between a special Higgs boson, the supersymmetrical Higgs boson, and dark matter. Could we imagine, I don't know, to detect it in CERN or not at all, and why?
So can you hear me first? Yes. So indeed, in the searches that are done at CERN, so remember we were telling you yesterday, you do these collisions and then you create all kinds of things. Then what we do is that there are some theorists who build models, and some of these models predict that you can have some interactions between these dark matter candidates and the ones that we know, so from the regular matter. So to give one example, I think you had it in your slide, there's something called the dark photon, which would be kind of the partner of the photon, so the photon that you know from the light. So the dark photon would talk to the regular photon, and then they would decay, and then we could see them this way. At the moment, we haven't, and when we don't see something, we put what we call limit to say this could exist, but not beyond this energy, or we kind of reduce how it works. And then this goes back to the theorists who kind of try to either improve the model or invent another one, and so on and so forth.
Thank you. And now I turn to Enrico. And I'm sure you saw the last slide where Ed told that maybe how can we know about the beginning of the universe when we cannot understand our own brains? And you are the biologist in the room, and I was wondering if there is any sense in comparing the complexity of our brains and the complexity of the universe, or are we just comparing, I don't know, oranges and apples here?
So you're asking a complex question, right?
Because it's a complex topic.
Which is more complex, the brain or the universe? And in a way, it depends on how you look at things, okay? So in some sense, everyone sitting here, as Ed pointed out, is a product of the universe. We're all stardust, so in a sense, we are the consequence of the universe, and so the universe is more complicated than us because it contains us. On the other hand, our understanding of the universe depends on our brain, on Ed's brain, for example, which has been beautifully illustrated today. And so in that sense, the universe, our understanding of the universe is limited by the complexity of our brain. So in a sense, it's an issue of perspective. However, I think maybe Ed was saying, I think, was making the general point that we can study very complicated systems by making simplifications and using certain approaches like the perturbation theory. And that applies to the brain, it applies to the universe. It's a fantastic thing that we can make sense of very complicated systems by making simplifications which ultimately reflect the symmetries in the systems that we can assume. For example, I'm not an astronomer, cosmologist, but you might assume that every star is equivalent to every other star, and they may have certain properties. You don't have to, you make simplifications which reflect the symmetries, the fact that at certain levels, you can see similarities between different things, and you don't need to treat every star as an individual star, or whatever, how many billions there are. In the same way with the brain, we have neurons in the brain, and we can make generalizations, we can say, try and understand general behaviors. So actually it reflects the symmetries and the simplifications that we can make. But I don't know if that's a correct a summary of what Ed was trying to get at.
I mean, I think I was just basically trying to say the brain's complicated. And to try and understand processes within it, we're still learning, right? We're still, and there are various processes. I mean, I know of talking to my MRI colleagues who look at brains all the time, that there's only so far they can take the analytic elements of it before they basically have to just look at the data and try and infer something from it, but they can't predict it, for example. It was at that level. Yeah.
Thank you very much for this answer. Et je me tourne maintenant vers Camille pour savoir si on a beaucoup de questions qui nous viennent de la plateforme en ligne.
On a beaucoup de questions en ligne, oui.
On a beaucoup de questions. On va peut-être commencer par en prendre quelques-unes, peut-être 2 ou 3 à la fois, si on en a plusieurs.
D'accord. So the first one is there a center in the universe, and are we moving with respect to this center?
Yeah, it's called Huddersfield. It's where I was born. No, there's no center. There's no center. In fact, Daniel made a really nice, in answering a question last time, he pointed out that we think of the Big Bang is a poorly named concept, and indeed it was introduced by Fred Hoyle in a radio broadcast. He hated the Big Bang. He hated the idea of the expanding universe. And so he dismissively called it the Big Bang as a way of, and it took off as a description. But rather than it being an event in space, it's an event in time. It happens everywhere in time. And then objects are moving apart relative to one another. So it's an event in time rather than an event in space. Space could well be infinite, in which case it's happening everywhere. So it isn't there isn't a center to it. Yeah.
And then there is a question about supernovae. So you said that supernovae are standard candle. How can we believe that there are standard candles over billion years of the history of the universe?
Okay, this is somebody who's been knows a bit about supernovae. So the special property of type 1a supernovae is that they are, what happens is you have what's called a white dwarf, which is a particular type of star, and it's accreting matter from it's orbiting, and it's got an accretion disk around it, and it's accreting matter onto it. And Chandrasekhar, a phenomenal Indian theoretical physicist, worked out that if it accreted, I think it's 1.4 solar masses, it would explode. And what we believe is that is independent of where you are in the universe. That's the assumption we're making. So that when a type 1a supernova goes off, we know its mass. It's 1.4 solar masses. And it goes bang. And then we know how much light it's going to have. It's 1.4 solar masses worth of light. And then we detect light. We don't detect as much as that, and that's because the intensity of the light drops as it travels. But by measuring the amount of light, we can then work out the relative change there's been, and that allows us to work out the distance to it. But the assumption is that it doesn't change, but it is an active area of research to try and establish whether there is any evolution effects in the type 1a supernova. And as far as I'm aware, they haven't seen any, but I'm not an expert on it. But it is a very active area of research.
Peut-être une troisième, du coup?
Okay.
Oui, si on
So there is one about dark matter. So it's so difficult to see dark matter. How do we know that it's not a new force of physics or a constant that we could add? How do we know that it's really dark matter?
Dark matter. Take the mic.
I can try. So I forget if both you and I think Daniel mentioned dark matter, and the way that we saw it was in indirect way. So what we saw was not it directly, but we saw a consequence of it, because the one thing that we know about it is that it cannot escape gravity. So this much we know. And then depending on the models, so the one that I was mentioning earlier, the way that it works when you, so this is one example, there are many examples, but in the one example that I mentioned, the way that you describe it is that you add terms in your theory, and these terms, they're also bosons. So you can think of this dark matter also as something which is like a new interaction, which would have new particles. So in some sense, I think this could answer your question, because we know one thing is that it's sensitive to gravity, and then all the rest that we are trying to prove is by testing the specific models. I would say, I don't know if you want to add something.
That's one way, and there's another way which I think, which is you say, maybe we're not understanding gravity. And these come under the generic titles of MOND theories, modified Newtonian dynamics. So in principle, what they're actually modifying is Newton's laws. And they say Newton's law is valid out to some given, it's not necessarily a distance scale, but an acceleration scale, and then it gets modified. And it's an empirical thing. They just modify it. And so you don't need any dark matter. You've just changed the law of the force law. And now you just have baryons. You and me, we're back in the galaxy. And in fact, they're remarkable fits to the rotation curve that I showed to you. It was introduced by someone called Milgram and back in the 1980s. And it fits the rotation curves really nicely. And so there's a lot of interest in this. But one thing about cosmology is, because it's taking you through the universe, right? It's taking you through a historical, when you look back, you're looking back in time. It's not good enough just to fit the rotation curves of the galaxies. You've got to also be able to fit, do you remember I showed you the clusters of galaxies? You've got to be able to fit that. You've got to be able to fit the cosmic microwave background radiation. You've got lots and lots and lots of things your theory has to fit with. And whereas dark matter has been remarkably successful in fitting these, the MOND theories, they fit some of these and then they don't fit the others. And so that's the nature of research, right? You're pushing them, and then so people are still actively working on MOND. A very good friend of mine is working on it, coupling it to some sort of matter to see what happens. But I'd say at the moment the dark matter paradigm remains the best fit overall.
Thank you. I have many questions. I could go on for hours, but I'm sure our audience also have many questions. Donc je me retourne vers vous dans la salle. Est-ce qu'on a des petites questions dans la salle à poser à nos trois intervenants? Alors peut-être d'abord ici et ensuite au milieu. Voilà.
Merci. Thanks a lot for the very inspiring talk that triggers our imagination. I have a question about actually, if I understand correctly, the small quantum fluctuations at the early phase of the universe ended up giving big, huge galaxies. And my question is, what do we know, what's the origin of these small quantum fluctuations initially?
Okay, so they don't directly give the galaxies in that. It's not that they become so big, they're as big as the galaxy, and therefore the galaxy forms. But they get magnified up so that they're enough to give. Do you remember the hot and cold spots on the microwave background? So they're the seeds for those. And then those are fluctuations in effectively the gravitational pull in different regions of the universe. And then matter that's passing through those regions, that then gets pulled in. So the fluctuations are providing those seeds that then lead to the matter then collapsing into those regions. So we introduce a field, a scalar field. The closest, we've only ever discovered one fundamental scalar field, and that's the Higgs field. So a scalar field is an object which has got a value everywhere, It can change in time, but it doesn't have a direction. So a temperature is an example of a scalar field. It's not a fundamental field, but you say the temperature is whatever it is here, 20 Celsius, and over there it might be 18 Celsius, but you don't say it's 20 Celsius in that direction. That's a vector field. So these are scalar fields, and they have basically an internal energy, which is we call a potential, and it's evolving down its potential from high energy to lower energy, and as it does so, it's fluctuating from quantum fluctuations. So in some parts of the universe, it gets fluctuated up the potential, and in other parts of the universe, it gets fluctuated down the potential. And that's where you begin to get these distortions in the space-time. So that's the basic idea behind it. Yeah.
On avait une autre question au milieu. Monsieur, ouais, si on peut donner le micro.
Thank you. Yes. Well, thank you for this brilliant talk first. I'd like you to expand a little on what you said before about the beginning of the universe. I would say that most of us think of the Big Bang as some kind of explosion. Yeah. But from what I understand that you were saying is that's not the case. Everything happened at once. Could you tell us more about that? Thank you.
I think just from the language you've used there, right, you're thinking of it as an explosion, and as the question was, and it's how many of us think about it from a point, which means there's a center, right? So where in the universe is the center? The idea is that what we do not know is what banged. I said it yesterday. What caused it? That for the universe to emerge. But the idea is that something, some energy, Hawking would have argued it's just a quantum fluctuation. He used to, when he talked about something called the wave function of the universe, which is a way of describing quantum mechanically how the whole universe might have emerged, he said it was just a quantum fluctuation. It can happen at any moment. And it inputted some energy, and then that energy caused the space-time to begin to expand. So the idea is there's some input of energy, don't know where it's from, that's one of the big issues, but it's then once it's in there, then the space-time that's been created there, because time has been created, it's at an instant of time, it begins to emerge and grows from there everywhere at the same time. So it's not from a point. That's the idea. Not from a space point. Okay.
Before we get back to... please, go on.
I'm going to have a go at talking about something I know nothing about, which is actually what I do most of the time. So I'm trying to understand what this means, this expanding universe, this Big Bang, and yet it doesn't have a center, and it doesn't... So imagine this lecture theatre was an infinitely large lecture theatre, all right? And it went on forever. But then, and we're all sitting here in this lecture theatre, and then all of a sudden, we start to move apart from each other. Okay, so we start to think, my goodness, this lecture theatre is getting bigger and bigger and bigger. And all of a sudden, you are moving away from me, and your neighbours are moving away from each other's neighbours. All right, and that's happening in this lecture theatre. But actually, this lecture theatre is infinitely big. And so there is no centre to this process. All we're aware of is that everyone's getting very far away from everyone, very, very fast, and it's probably very, very hot as well. So that's my image, my attempt to understand the Big Bang. So that when that started is the Big Bang. I don't know if that's correct, but anyway, that's the way I would think about it.
Ed, is that correct?
Brilliant.
Perfect.
You can see why Enrico's a fellow of the Royal Society, right?
Maybe at this point we should ask you to rename the Big Bang and come up with a name which would make...
Don't push it.
Thank you. Before we go on to the online questions, I have a quick question for you, Ed. You mentioned the gravitational waves and the huge impact the discovery has made. And my question is related to one of the dark matter hypotheses you told about, primordial black hole. Could we maybe have some hints of the existence or not of primordial black holes using gravitational waves, and how?
Yeah, I mean, so when the discovery was made back in 2015, and then within a year they'd found quite a few more, and each time I mean, it is really, really remarkable. I mean, no one was expecting this. I think it's fair to say no one was expecting to find black holes orbiting one another that were so big. They're 20, 30, 40 solar mass black holes orbiting and then colliding. And there was no known mechanism, and I think there's still not guaranteed, there's people still working on it, why these black holes are so of this size, are in a vicinity where they're orbiting one another. And they've found 150 or more now of these. And so one possibility that a guy called Mark Kamiankowski came up with within a few weeks was that maybe what we're seeing is primordial black holes, that these are where it is possible to form them this size, because that just depends when they form in the universe. But as I just mentioned about cosmology, it's one of the big advantages of being at a place like CERN, where you've got the Large Hadron Collider. You can repeat the same experiment over and over and over again. But we've only got the one universe. But the big advantage of having one universe is you can look back in time. So you basically have a time machine. You can look back. And so as soon as these were put forward as possible candidates, people then started saying, well, okay, if they're the candidates that are giving us the supernova, the black holes that we're observing, they will have had other consequences earlier on. And they will have given us, maybe they give us the dark matter. And by looking at constraints on dark matter, you can basically rule these out now. And it's very unlikely that the black holes that we're seeing is primordial. But that doesn't mean they're not there, that primordial black holes. I'm spending ages of my time trying to work out the distribution of primordial black holes in the universe. So I hope they're there, but they're just not likely to be these.
Thank you very much. Camille, est-ce qu'on a d'autres questions en ligne sur la plateforme?
On a des questions en ligne, oui. So somebody is asking if it's really necessary to unify gravity and quantum mechanics.
I would have said when I began, it was the thing to do. It was the reason. I was at Imperial, and I was lucky enough to be there when a remarkable physicist called Abdus Salam was there, and he was still well. And so he would present a slide. Abdus Salam, along with Weinberg and Glasgow, unified the electromagnetic force and the weak force into the electroweak force. And the idea, in fact, I think, was it Daniel? Did you have this? I think Daniel had a slide on where he showed as you go to higher and higher energies, you try and unify the forces so that there's one mathematical description of all the forces. And even though we clearly experience different forces today, you wouldn't say that electromagnetism is the same as gravity. The idea is that in the very early universe, they've unified together. Now, that was definitely, when I was a PhD student, that was what the goal was. And I think it still is a goal for many, but for far fewer people now, I think it's fair to say. And so I still like the idea, but I think it's now become less of a dogmatic, we need to demonstrate unification.
And then there was a question about neutrinos. So you said that neutrinos do not interact with matter, so how do we know they exist?
So they do, very weakly. So to try and find neutrinos, what you tend to do is you go deep underground and you build a big detector that will maybe has heavy water in there, is that right? Which has sort of got a higher density of nuclei, and you hope that, I don't know, is it a few a year? It's very rare. A neutrino will come in. Normally it will go straight through. It's first of all got through all the rocks, so that, why underground? It's to stop things like cosmic rays getting all the way through, because they can mimic neutrinos, and we know about cosmic rays, so you go deep underground, so any cosmic rays that are coming into the Earth get absorbed by the time they've reached the detector underground. But the idea is the neutrino comes in, it hits a nuclei, and it just pushes it a little bit. Neutrino then carries on, and it transfers a bit of momentum to the nuclei, and the nuclei then creates a phonon, and the phonon works its way through the liquid, and there's banks of detectors, and they pick up a little shower of light. And they've got a way of doing it so that they can reconstruct the path of the in fact, you were telling us about this. I'm just, why am I doing this?
You're doing really
They can reconstruct the path, so they can see where the neutrinos come from. There's a phenomenal neutrino. In fact, now I'm on a roll. There's one in Antarctica, right, called Ice Cube. Ice Cube is they have drilled into 2 or 3 kilometers of ice, and they've put lots of detectors basically on ropes. I don't know what it's made of. Lots of them. They've made a grid out of this, 2 or 3 kilometers down, and they look for neutrinos which have come out through the sun, shot through the Earth, and interacted, and they can also look for cosmological neutrinos that have come from way further in the universe, and they're seeing them. Not many, but because they interact so rarely, but they do interact via the weak force.
Thank you. Est-ce qu'on a d'autres questions ou je continue?
Oui, une autre. So about the expansion of the universe. What is happening when the universe is expanding? Is it getting colder or warmer?
Oh, that's a good question. So I showed you the cosmic microwave background radiation. So when it was released, when the atoms formed, the temperature was very high. And then imagine a box, and you've got some radiation in the box, and now you double the size of the box. What happens to the radiation? It cools down. And you keep doubling the size of the box, and the radiation cools down, and that's what's happening. So the radiation, which was very hot when the atoms were first formed at 380,000 years after the Big Bang, as the universe has expanded, and it's now much, much larger, the radiation's cooled down, and it's getting colder and colder as the universe expands. In fact, basically the temperature is basically inversely proportional to the size of the universe.
Oui, j'ai vu que deux mains se lèvent dans le public. Si vous pouvez, d'abord devant et ensuite derrière.
You were talking about the Higgs boson as being a field. We don't know much. I mean, there is still questions about what gravity is. Could gravity be also a field? And you were also talking about gravitons, but did we find them or not? So can you tell us more about gravity and what it is?
We would think about gravity as a field. We would, in an ideal world, we'll be able to quantize gravity, just as we can quantize photons, light. It's called quantum electrodynamics. It is the most precise theory we have. The agreement on various processes between experiment and theory for quantum electrodynamics is to 1 pi and 10 to the 13 or something like that. So ideally we would like to quantize them so we can understand the quantum mechanics. We've done it for all the fields, but we haven't been able to properly do it for gravity. But that is a goal. And the associated quanta is called the graviton. But we certainly think of gravity as fields. I mean, classically, that's what even Newton thought of it as fields. So just as we think of electromagnetic fields, we think of the gravitational field. At school, you learn that the gravitational potential of the gravitational field goes as 1 over the separation between objects.
Thank you. Et la deuxième question, peut-être. Ah, vous n'avez pas fini, pardon.
But as we see that light is a wave and also particles, could it be the same with gravity?
Yeah, that would be the idea.
Oh, okay.
Yeah.
But we haven't proved this yet.
It's called a wave-particle duality. Yeah. It's another form of symmetry, actually. Yeah.
Et on va prendre une toute dernière question derrière. Désolée, ce sera la dernière.
Bonsoir. Alors j'avais une question par rapport à l'expansion. Est-ce qu'elle respecte cette théorie de la symétrie de l'univers? Et si tel est le cas...
I will translate. No worries, I will translate. You don't have to worry it. Continuez.
Alors, si tel est le cas, est-ce qu'on en sait plus sur l'axe de symétrie de l'univers?
So the question is about, does the expansion plays by the kinetics of the universe? Donc, est-ce que l'expansion suit la cinétique de l'univers? C'est ça votre question?
Exactement, oui.
Yes, does expansion follows the whole kinetics of the universe?
Does the expansion follow the kinetics?
Yes, is it the same movement, the same kinetics?
So we think the expansion is due to the energy that was put into the universe, and as that energy, it's in sort of a number of different forms. There's the energy from the radiation, and there's the energy from the matter that you and I are, and the energy from the dark matter, and there's the energy from the dark energy. And there might even be energy associated with the curvature of the universe. They all provide energy contributions, and the way the universe expands is dependent on the sum of these energies. And it's called the Friedmann constraint. It was the same Friedmann that I showed you at the beginning. He wrote down the equation that tells you how the universe is expanding as a sum of all the energies, and what determines the rate of the expansion is which of these energies is winning. And in the very early universe, radiation is winning. And so that dominates the way, that determines the way the universe expands, and then eventually that drops off and the matter begins to take control, and that changes the way the universe expands. And then the point today is that the matter has dropped off, the radiation has dropped off, and it's the dark energy that's now driving the expansion, and it's driving it so it's accelerating. Whereas with radiation and matter, the universe was decelerating. It was slowing down. It was expanding. It's like being in a car, moving along the road, but you've put the brakes on. So you're still moving in that direction, but you're slowing down. But actually, what the universe is doing today is moving in that direction and going faster and faster. And the big question is, what is the energy, the source of energy? What's the petrol or the electric battery, whichever you want, that's driving it?
Thank you.
Does that help?
Does that answer your question? Ça répond à votre question? Thank you very much. Before we wrap up, I will ask one very last question. Ed, you mentioned earlier that the early universe had some irregularities, some ripples, and so we can see today from the cosmic radiation background. And my question is, we can do a comparison because it's the same when you look at a snowflake. You need a tiny grain of dust at the beginning, an aerosol, to have the snowflake. So I was wondering, are irregularities required for the emergence of the Big Bang, the universe? Without these irregularities, what would happen? Nothing.
If I've understood you right, you're asking how can the universe emerge out? Structures emerge without the fluctuations?
What would have happened if we have having these tiny differences? Without them, what would have happened?
Well, you'll have if they're tiny differences, then you'll have a different distribution of the hot and cold spots in the cosmic microwave background, and you would have a different distribution of the galaxies. Now, whether that matters depends on the statistics of the distribution. Yeah, one thing I didn't say, when I showed you the hot and cold spots, you can't predict where those hot and cold spots are. You can't predict on the sky where they are. What you can predict is what their distribution is. It's a statistical thing. You can predict how many hot and cold spots of a given size do you expect in a region, or how close should these hot and cold spots be on average. And varying those perturbations leads to slightly different distributions. But we can measure that. And so that's precisely how we rule out, well, nearly all the models that I've worked on, but I don't feel bad about it, that's science, but you use that observation of what the distribution of these hot and cold spots are, you compare it with the statistical prediction from that theory with your changing perturbations, and you see if it's consistent or not. So there are still lots and lots of models of inflation which are consistent, but there's lots of models which have been ruled out because they're no longer consistent with those anisotropies that we measure.
Thank you for explaining this. Would you like to add something as a word of conclusion, either Yasmin or Enrico?
Sorry?
Would you like to add something?
No, I don't think so.
No?
He's already explained.
maybe there are symmetries too in biology, and maybe we can do some parallels. I don't know, between the irregularities, the symmetries at the very beginning. I don't know, of the embryo, and then when the cell is evolving. I don't know. Maybe you can. Maybe do you see some analogies or not?
I think I will talk about this tomorrow. So this is a good advert for you guys.
So come tomorrow.
And we can discuss the relationship between the symmetries we've been hearing about and the symmetries in biology.
Thank you very much. Merci beaucoup. It's 8 p.m. It's really time to wrap up. So please make a huge round of applause for our panelists and our speaker. Et avant de vous souhaiter une très bonne soirée, j'ai encore deux petites infos, deux petites choses à vous dire. Si vous n'étiez pas là les autres soirs, je vous rappelle qu'on a le spectacle Son et Lumière du Colloque Wright qui se déroule tous les soirs. Et même si vous n'avez pas pu y aller cette semaine, il se déroule jusqu'au 17 novembre au Musée d'Art et d'Histoire. 3 horaires, 18h30, 19h30, 20h30. Ça dure 20 minutes, c'est gratuit, donc n'hésitez pas à y aller. Et le deuxième rappel, je crois qu'on l'a déjà fait, le colloque n'est pas fini. Il continue demain à 18h30 avec la conférence du professeur Enrico Cohen, ici présent, qui va nous parler des symétries de la vie, des atomes jusqu'aux orchidées. Donc s'il vous plaît, revenez, n'hésitez pas. Et moi, je vous dis une excellente soirée et à demain. Merci beaucoup.